If we're talking about hype cycles, I reckon flow cytometry probably started its first hype cycle around about 1970, in the early 1970s, and probably came out of it in the early 80s, which would have coincided with the HIV epidemic. And even today, by far the biggest applications of flow cytometry is actually in clinical labs, particularly for general immunology. And still, by far, the biggest use is for CD4 counting in HIV patients. However, it hasn't had the same impact in drug screening. So particularly if you compare it with its sister, that's high-content imaging. But what I want to show over the next sort of 20 minutes or so is how that's changing and some of the dynamics, some of the things that is actually highlighting flow cytometry as a really good drug screening platform. So in case some of you need a recap, flow cytometry is a measurement of cells in a flow system which delivers cells singly past a measurement point. In other words, it's a single cell or single particle detection system. And it does this by taking a cell suspension and introducing it into a rapidly flowing sheath or sheath fluid in a specially designed flow cell. In this flow cell, or the design of this flow cell is such that the cells are focused or hydrodynamically focused, so they align themselves in the sheath flow and they can pass one by one through a focus of an intense light source. I've got a laser pointer somewhere here. Through the focus of an intense light source. As each cell passes through this light source, it gives rise to light scattering, and light scattering alone can give indications of certainly the morphology of the cells. And if the cells are fluorescently labeled with probes, fluorescent antibodies, it gives rise to fluorescence, and this fluorescence can then be picked up by a series of PMTs or photomultiplier tubes. Usually, flow cytometers have more than one laser. Some flow cytometers can have up to 5 lasers, and you can have a bank of 8, 9 or more PMT detectors, depending on the complexity of the instrument you have. And Lorenz also already mentioned that flow cytometers can analyze up to 70,000 cells per second, but it's more usual, for instance, to analyze between 10 and 20,000 cells per second. So because it analyzes cells on an individual basis, it's good to look at the heterogeneity of populations, and you can perform simple subpopulation analyses within complex samples. This is just an example of lysed human blood, and on the left here, we're just using the 2 light scattering signals, side scatter and forward angled light scattering. Side scatter is particularly sensitive to the granularity or the internal content of cells, whereas forward angle light scattering is more sensitive to the volume or the size of the cells. And by just using these 2 parameters, we can actually get an idea of the various subpopulations in human blood. As you can see here, these are granulocytes. As you know, they're more granular, so they're more sensitive to the side scattering parameter. Likewise, if you label these with specific fluorescent antibodies, in this case we've labeled it with an anti-CD45. CD45 is the common antigen leukocyte. You can then start to actually tease out more and more information from these populations of cells. Now, Lorenz has already touched on phenotypic screening and some of the applications of flow cytometry. Now, talking about the hype cycles, with flow cytometry, some changes in technology has started to sort of bring it back into the forefront of drug discovery. But the current sort of AIDS crisis for flow cytometry is this. It's this appetite, this new appetite for drug companies to do things all phenotypic. So this is really pulling flow cytometry into the field of drug screening. because it's an ideal platform for measuring phenotypic cells, or looking at it's an ideal platform for sort of physiology-based or phenotypic drug discovery. And it's particularly relevant when you're using disease-relevant cells. It's multiparameter. It can analyze several parameters from the same cells at the same time. And this is really important when we're using rare phenotypic samples, because your sample is the most precious item you have. So the more information you can get from it, the better. And that'll obviously significantly reduce costs as well at the same time. Now, we've already alluded that flow cytometry isn't a new technique, and in fact it has been used throughout the whole drug discovery cycle. It's used throughout all phases, drug discovery and safety and clinical diagnostics. But most flow cytometers still have single tube sampling mechanisms, and these are designed for large volume clinical samples. And this impacts or affects the sample throughput. A few years ago, flow cytometer manufacturers started to develop plate-based flow cytometers, and this increased sample throughput and enabled more routine applications in drug discovery. And of course, this is aided by peripheral automation and liquid handling. Excuse me. At GSK, we originally started off by using a few plate-based flow cytometers. In this case, it's a Beckman Coulter FC500, and we automated this with a robotic transfer system connected to a plate stacker. And with this system, we could stack up to 40 plates in this refrigerated stacker and run the instrument overnight or even over the weekend sometimes. However, the throughput was slow and low. A plate would take at least an hour to run, and often longer than that. Sometimes it took 2 hours. Hence the reason why the refrigerated stacker was important, not just because of the fact that you set up an experiment late on a Friday afternoon, come back on the Monday and find out it's actually stopped halfway through it. But anyway, with that system, we had some success at doing some routine drug discovery, particularly for target-based drug discovery. And the table here just shows some of the examples of some of the assays that we ran. I'll just choose one example. And it's a routine assay that we were using flow cytometry, and this is to look at T-cell receptor-stimulated phospho-AKT or AKT phosphorylation in T cells. Cells, in this case, T cells would be treated with compounds, stimulated with anti-CD3, anti-CD28, fixed, pimbolized, and then labeled with phosphor-specific antibodies. With this system, we could actually detect the effect of active drugs. What we have here is, if we look at fluorescence, which is the AKT phosphorylation, against size or light scatter. With no or low compound treatment, you can see that a large portion of the cells contain phosphorylated AKT. And with increasing concentration of kinase inhibitor, we can see that there are fewer and fewer cells containing phospho-AKT. Now, if you notice here that the number of cells which have phospho-AKT is actually quite low. Now, this is quite normal when you're looking at cell signaling events or protein phosphorylation in cells. So this is one of the reasons why flow cytometry was really the only technique we could use to do this. A standard MSD platform just isn't sensitive to be able to detect these low numbers of cells containing phosphorylated AKT. Anyway, we could use this data to plot standard dose response curves. This is the effect of the pan-kinase inhibitor LY294002, and then report that data to our various database libraries. Now, interestingly, if you use this cell-based data along with standard biochemical or enzyme-based data, you could start to see some interesting correlations. And two things I'd like to point out here is that if you look at these drugs along here, which have very high enzyme activity, but no cell-based data, it indicates that these compounds here most likely having penetration effects. And likewise, these compounds here don't have any enzyme activity, but have a high cell-based activity, showing that these are most likely an off-target effect. So I mentioned throughput limitations, but still, flow cytometers are often the go-to instrument of choice in drug discovery labs, and they tend to be used for sort of early target identification, validation, particularly when using rarer or human animal cell populations. The data is often more physiologically relevant, but however, the throughput itself limited its application to screen larger sets of compounds. Instead, what normally happens is new high throughput assays are developed. These involve less physiological relevant recombinant assays, and these often involve expensive proprietary reagents and kits. But often you see flow cytometry reappearing later in the program critical path. Now, the rate-limiting step with flow cytometers is the actual transfer of the sampling probe from one well to another and the mixing steps afterwards. This often takes several minutes. But some work done in Larry Sklar's lab at the University of New Mexico developed this innovative sampling technique. It's called a hypersite robotic sampling device. And introducing this into the flow cytometry process significantly increased the throughput, thus making flow cytometry a high throughput instrument. And obviously, if you use this with other automation equipment, it has a significant impact on throughput. Now, in a conventional flow cytometer goes into the sample, samples the cells, the data is acquired, the information is acquired, the data is then saved, and then the actual sample probe goes through these various flushing steps. However, in the hypersite, what happens is that the probe goes from one well to another rapidly, and each time as it comes out of the well, you get an automatic introduction of an air gap. And the software is clever enough to use to actually identify what is a bubble and what is a well. So here you can see a number of events versus time, and as the sample goes through, you can see a number of cells come up, and then as a bubble goes through, there's no cells coming up. So this time-based AutoGating can be used to actually identify the wells or separate bubble from sample. And with this system now you can analyze plates in less than 5 minutes. It always depends on the cell concentration, of course. 3 or 4 wells in less than 10 or 11 minutes. More importantly, you can use really, really low sample volumes, again, saving your sample. So, hypersite data analysis also differs from conventional flow cytometer. For start off, the system now thinks it's actually analyzing just one big sample instead of, say, 96 separate samples. So you have to do 2 things. And the first thing you have to do is actually remove the noise or remove air bubbles. And the flow cytometry or the hypersite software allows you to do this. Once you do that, you can identify your wells, and here you can see all 96 wells. Okay, and then you can do your conventional flow cytometry analysis, and that's identify your cell populations. In this case, this is all well data, but you could choose to do single well data if you want to. And of course, then you can do further analysis. You can look at each well separately, produce heat maps. You can have your Excel outputs, plot the curves, and report the data to your databases. At Stevenage, we have 2 hypersite systems linked to 2 different types of flow cytometer. One is an Acuri C6. It's the standard flow cytometer used in the IntelliSize systems. And we also have a more complex laser-based, a more complex flow cytometer which has 3 lasers in it, and this instrument can analyse 70,000 cells per second, so that's increasing throughput even more. Both these instruments are integrated to Biomex, and we have a little shuttle which transfers plates from the deck into the flow cytometer, and we can process 20, 30 plates at a time. So, what have we been using this system for? Well, one of the things we used it for is to do a primary cell focus screen. Now, this is a complex assay involving PBMCs where we wanted to look at up to 3 different parameters in stimulated T cells within PBMCs. Now, there are several signaling pathways leading to the endpoint we're looking at. We didn't have any prior knowledge of which pathways were involved at any one time. So there wasn't any other technique available to us to actually look at these pathways or any of the targets involved. So flow cytometry was really the only option we could actually use. And we managed to run a 60-compound, diverse compound screen. This is a well annotated compound set, so we already knew a lot about it. We could read plates in 10 minutes, and the actual QC around each plates was excellent. This is shows you a typical output of the screen after hit follow-up. And what we have here is compounds along the top. There's a compound concentration. Each box represents the parameters we're looking at. So there's 3 target-based parameters, okay, and the top one here is where we're actually counting cells, or at least counting T cells. As you can see, this is information-rich, and simply by taking just by taking the effect of compounds on cell number, in other words, toxicity, we can actually decide whether a compound is a true hit or not. As in the case here, this compound here is active against the target we're looking at and has no toxicity, whereas this one here is coming out as a false positive simply because it's significantly reducing CD4 counts. And this data isn't lost because for other similar assays using PBMCs, we can use this same, particularly this toxicity information, and help annotate these compounds. So these compounds and their effects on TC4, the information can be used for other screening campaigns. We're also using the hypersite just for doing normal routine target-based assays, and this is just an example where we've been using it to look at CD11B upregulation in Grow alpha stimulated whole blood. CD11B is a surrogate for chemotaxis, and as you know, chemotaxis is a rationale behind a number of anti-inflammatory drug discovery programs. What we can do with whole blood is stimulated and treated with a compound, then fixed and lysed and labelled with a specific neutrophil marker. And just using light scatter and CD16, we can identify our population of neutrophils. And in this neutrophil population, we can look at the upregulation of CD11B and obviously look at the effect of inhibitors on Grow alpha stimulated neutrophils in whole blood. Now, what's really significant about this is that we can use as low as 10 microliters per well. In fact, we've actually been lower than that, and assays like this can be configured to 3 or 4 well formats. Another area where the hypersite is being used is for monoclonal antibody screening. Now, screening of hyperthermal supernatants for specific antibodies that bind cell-based antigen is a critical component of monoclonal antibody generation and is often a bottleneck. And it's preferable to look at binding of the protein to cells expressing their protein, because these proteins are in their native state, and this tends to be preferred over normal solid phase methods. Now, since thousands of clones are routinely screened, flow cytometry was not viewed as a practical option for primary high-throughput hybridoma screening, and was often just used as a secondary screening method. However, the hypercyte now brings that monoclonal antibody screening through to its to a primary phase. Now, it's usual when doing hybridoma screening to actually check the cross-reactivity of your secreted maps against other species or different types of controls. You know, for example, human, cyno, mouse, or negative controls. But because flow cytometry can be multiplexed, you can use a process known as fluorescent cell barcoded. And what we can do here is we can actually take the various cells expressed in the protein, label them with different dyes or different dye concentrations, right? Mix them together with a supernatants, and then actually detect binding of the cells in the same well. This, of course, saves time, reagents, and it'll give you more like-for-like tests. Because normally what would happen, they would actually run 3 or 4 separate assays. Let's just give you an example of the output. Here the cells have been processed. They've been labelled with different concentrations of calcium, mixed, and they've had the supernatants added to them. And from here you can see that when you plot these on a flow cytometer, you can clearly distinguish the separate populations. And from each of these populations, you can actually then start to identify the expression and the binding to the proteins. So, like you can see, we've got the as we would like, equal binding in cyno as we would in human. So, in summary, then, traditional flow cytometry has had and is still having an important role in the drug discovery cycle, and as I've shown, it can be represented at each phase of that cycle. Often flow cytometry is a preferred technology to use in drug screening when running phenotypic assays, but throughput limitations has led to the development of less desirable recombinant-based assays. The introduction of plate-based sampling flow cytometers began to realise the potential of flow cytometry as a drug screening tool. Now, the introduction of faster sampling technologies such as the hypercyte and the use of peripheral automation and liquid handling has transformed flow cytometry as a drug screening tool, and now it doesn't look out of place in a drug screening lab. And I don't know whether it's been through or whether it's going to go through another hype cycle, but it's looking good for phenotypic drug discovery, at least. So what's the future? All right, it's still at the lower end of the drug screening capacity, where 1 to 2 million compounds can be profiled in a couple of weeks. There are strides in increasing the throughput of the technology even more, and now you can get 1536 well plate sampling. But like Lorenz alluded to in one of the questions he was answering, it's not just about throughput, and you have to consider assay costs and cell supply, particularly human primary cell supply. And often it's the actual biology that limits the throughput itself. For instance, it's difficult to replicate many primary cells in 384 well assays. Going forward, as the data gets more and more complex, we need better computation analysis tools to handle quantity and complexity of the data. Its sister high-content imaging has made huge inroads into that space, and flow cytometry will be catching up soon. There are some systems in place which are available now, and indeed we're looking at these systems at GSK. There are tools, commercial tools such as Cytobank and Plate Analyzer, which are helping these. So that's it. Thank you.